This is the third video identifying chiral centers in more complex organic molecules. This is the same molecule represented in two different ways. One is the skeletal line angle structure. The other is a three-dimensional ball and stick model. And on close inspection, these two are actually mirror images of each other, and I'm not sure why that's so on this website. It may be a rare error, but everything's in the right place and connected the right way if you go through. You can see a benzene ring connected in to this. Do you recognize this functional group here? It's an amide, and you can see the amide there. Here the amide's going towards the back, or no, coming out more towards the, well, it's going down with the oxygen going towards the back. But this hydroxyl group is coming towards the front, where here it's aimed towards the back. So there's some discrepancies, but the connections are all the same. And you can go through and find every atom in this ball and stick model represented in this line angle structure. So how can you quickly go through and find chiral centers? You'll find with these big molecules that you can tell very quickly. So first I'm going to go through, and the highlighting I'm doing here is a little backwards. I'm going to highlight the things that are not chiral centers. Everything connected to a double bond. No chiral centers on any of those atoms. Everything out on an end. No chiral centers on any of those atoms. O's and N's, they only connect to two or three things. So no chiral centers where we have an O or an N. No chiral centers where we have two or three hydrogens. So here they're two hydrogen. Here there are three, here there are two. All of those are out. We're left with very few possibilities. I'm going to circle these in faint lines. So very quickly, we went from a large molecule with around 50 carbons in it to having just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible chiral centers. One of those we can eliminate because it has two methyl groups. So now we've just got 10. If you look at these 10, there's some things you'll notice. This one has a dashed bond going away from it. This has a dashed bond going away. A dashed bond going away. A wedge. A dashed bond. A wedge and a dashed bond. A wedge. A wedge. A wedge. A wedge. Every single one of these possible chiral centers also has wedges or dashed bonds that tell us something about the direction the atoms leave that, the bonds leave that atom. Well, let's check it to see if they're all chiral. This one here has the N, 2 different carbons, and an implied hydrogen. So yes, chiral bond. This has 2 different carbons, a hydroxyl group, and an implied hydrogen. Yes, chiral. This has 2 different carbon atoms, an oxygen, and an implied hydrogen. Yes, chiral. Going on, these 3 carbon atoms are all different, and the oxygen, chiral. Oxygen, 2 different carbons, implied hydrogen. Yes. Ruled out that one already. This down here, oxygen, 2 different carbons, implied hydrogen. Methyl group, 2 other carbons that are not symmetrical, a 4th carbon that's not symmetrical. Yes, it attaches to 4 carbons, but it's a chiral center. I missed one. We haven't done anything with this carbon. It's got a ring going this way, 2 rings coming off below, a different ring going to the left, and an implied hydrogen. That's a chiral center. It's our only chiral center that does not have a wedge or dash coming off of it. Going here, 3 different carbons and an oxygen, chiral center. Oxygen, 1, 2 carbons and an implied hydrogen, chiral center. And finally, oxygen, 2 different carbons, implied hydrogen, chiral center. So we have identified 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 chiral centers. Now I'm going to take a moment and just go through identifying functional groups. If you're good with functional groups, you've seen everything on chiral centers that I'm going to record in this video. But I'm going to look for functional groups in both these structures. So here we see these flat 6-membered rings. That's a really good sign of benzene groups, and we see 3 benzene groups on the left as 3 benzene groups on the left as well. So 3 aromatic groups. We see nitrogen. Nitrogen, we want to think amine, but when you see a nitrogen, you need to look what it's connected to. It's connected to carbons, and the carbon below it is double bonded to an oxygen. That makes it an amide. And that amide would include this nitrogen and hydrogen and the bond to this carbon and this oxygen. It's also going to include this carbon over on the other side. So the nitrogen is bonded to 2 carbons. It is a secondary amide. The oxygen we already included in the amide. We go up here, hydroxyl group. That's good, but we ought to check. Is this carbon bonded to anything but carbon and hydrogen? No. So this is a hydroxyl group. We've got one there. We've got another here. Another here. We have 3 hydroxyl groups, or 3 alcohols. Double bonded oxygens could be ketones, but we saw how one's an amide there. This one, instead of being an amide, looks like a carboxylic acid, except it goes to a carbon, so this is an ester. And we see the same double bonded oxygen, carbon, oxygen to another carbon. There's another ester. The same here. 3 esters. The same here. There are 4 esters in this. Now, we do have one other double bonded oxygen right here. And it goes to a carbon, and that carbon goes to only carbon. So this one here is a ketone. We've got this oxygen unaccounted for. It's in between 2 carbons. It is an ether. This double bond over here we haven't accounted for. Double bond from carbon to carbon, only carbons around it. It is an alkene. So I've accounted for all the functional groups with heteroatoms, N's or H's, N's or O's, and our double bonded group here, and our aromatic groups. And I think that's everything, but you could do this more systematically if you hadn't previously colored over it like I had, marking chiral centers.